Welcome to CPE 350, Chapter 7, Binary Mass Diffusion, Section 7.1. We're going to be covering the first part of Example 15, transient diffusion in a semi-infinite geometry. And in this part, we'll just be non-dimensionalizing the governing equation and the boundary conditions. So in Example 15, we're examining diffusion of gas carbon dioxide into beer. In Example 15, we'll be looking at the transient diffusion of carbon dioxide gas into flat beer. The question asks for the concentration profile and the constraints and assumptions that we're making. Because we need a concentration profile, we know that we're going to need to define the governing equation. So, looking at the schematic, we can set our x-axis Because we need a concentration profile, we're going to need to use a governing equation. Sketching out a schematic of the scenario, we can define any position to be z equal to 0, but it makes sense to do so at the liquid meniscus, which is where the A and B species meet. So we'll do that. We have no chemical reaction, so we're probably going to be using density or mass fraction units. And we can write our governing equation. So we've got an accumulation term, which is because this is a transient problem. And then we only have mass transport in the z direction. So we've just got flux in one term, and there's no reaction. Now, we can substitute Fick's law in for lowercase jaz. And when we do that, we get a first order derivative with respect to time and a second order derivative with respect to density. This means that we need two boundary conditions in the spatial coordinates, and we need one initial condition to describe the time derivative. So for our initial condition, we can simply specify that at time equal to 0, there is absolutely no beer. For our initial condition, we can specify that time equals to 0. There is no carbon dioxide whatsoever in the beer. So the concentration of A in B is 0. For our first boundary condition, we can note that this is For our spatial boundary condition, we can consider a semi-infinite geometry because the diffusion of gas into liquid is very slow and the gas is not going to penetrate very far into the liquid. So we can say that at a distance of infinity, the concentration of carbon dioxide in the beer is still 0 because it never penetrates to the bottom of the vessel. And finally, we can say that at the interface between A and B, there's some concentration, rho A naught, which we might not know now, but we'll call it a variable and leave it to solve for later. Next, we need to non-dimensionalize the governing equation and the boundary conditions, except we don't really have a clear time frame, and there's not a clear characteristic length in this problem. And so those two characteristics indicate that we could consider a similarity variable. So we define our similarity variable as the spatial coordinate over some characteristic spatial length, but we don't really have a characteristic spatial length if we think that geometry is semi-infinite. So in this case, we're going to define that characteristic length as a combination of the diffusivity and time. And when we do that, we This gives us the correct units for a characteristic length and allows us to create the similarity variable that contains both z and t. We include a factor of 4, which, if you didn't know to do so, it wouldn't be wrong. The reason it's there is basically because we have previous experience solving semi-infinite problems like this, and we know that it's quite convenient to have that factor of 4 to cancel out later. If you didn't know to include it, you just get to a point in the problem where you realized you kind of needed to multiply through by it, and you would go back and add it retrospectively. So we've non-dimensionalized our independent variables t and z, but we haven't non-dimensionalized our density. How do we do that? Well, the mass fraction is the non-dimensional form of density. And so if we think of the mass fraction as the density of A over some characteristic density, we can specifically define it as the overall density times the mass fraction of A divided by the overall density. So by this definition, our characteristic density is the bulk density of the composite. We can then differentiate with respect we can then implicitly differentiate both sides of the equation and solve for d omega A we can then implicitly differentiate, and we'll plug in that rho star is equal to rho, and we can then solve for d rho A over d omega A, and this is going to be useful when we non-dimensionalize the governing equation. So we'll just keep this in the cupboard for now. Next, we need to implicitly differentiate our similarity variable, and we're going to have to do this twice, once with respect to z and once with respect to t. So if we hold t constant, we differentiate with respect to z, and we only have one term that really takes any work, and that's dz. Now, if we do the converse and hold z constant, we have to differentiate with respect to t, and this takes a little more care because t is in the denominator and it's basically raised to the -1/2 power. So that -1/2 comes out front, and then t is raised to the -3/2 power. We can tidy up this expression just a bit more by taking 1/2 power of t under the radical, and that leaves us with 1 inverse power of t outside the radical. And of course, that means that term in the center is really just the definition of eta. And so we can dramatically simplify this partial differential by replacing eta for that middle term. Now we're going to solve for the useful partial derivatives, and if you're not sure what's useful, you can continue to non-dimensionalize the governing equation, and then you'll see what you need to solve for. But from experience, we kind of know we're going to want to solve for d eta dc at constant t and d eta dt at constant c. So we simply rearrange the above expressions to do this. Next, we're actually in a place where we can non-dimensionalize the governing equation, and I'm going to copy over on the right-hand side what these useful derivatives are that we've worked on in the previous slides. So if this is our governing equation, we'll start with the left-hand side, and we'll expand it using the chain rule so that we can transform the coordinates from rho t to to omega and eta. So we have already our expression for d rho A, d omega A, and similarly we have our expression for d eta dt. So we can substitute those into the left-hand side, and we can do a little bit of algebra here, simplify it, and there's the left-hand side of our equation. Moving on to the right-hand side, we expand the second derivative of rho with respect to z, and again we want to transform this into omegas and etas as our non-dimensional constants. Here we can plug in for d eta dz into multiple places. Again, we have our d rho a, d omega a already solved. Plugging those into the right-hand side of the equation, we get a slightly large expression here, but we can square the radical and get our right-hand side of the equation. Now we're at a point where we can plug both the left and the right-hand side expressions into that governing equation. So when we do that, we get a slightly larger equation that is actually simplifiable when you start canceling terms. And so that leaves us with a relatively straightforward equation. If we take the 4 over to the first derivative and put both derivatives on the same side of the equation, we arrive at our non-dimensional governing equation. So, this is now an ordinary differential equation because it's only one independent variable and one dependent variable. So we're keeping the tails on those d's straight. Next, we need to non-dimensionalize the boundary conditions. And here are our non-dimensional variables we've decided on. We've already done that. And here are the boundary conditions that we wrote out in real space. So to get these into non-dimensional space, we can make ourselves a little matrix here. For the initial condition, we're looking at all values of c and t equal to 0. So if we plug that into our definition of eta, we see that eta has to equal infinity. Likewise, if we plug in that rho a equals 0, that means that omega a also has to equal 0. So our final boundary condition is that omega a is infinity. So our non-dimensional boundary condition is that omega a at infinity equals 0. Turning to our boundary conditions, we have one at z equal to infinity and t all times. Plugging that into eta, we again get eta equal to infinity. And then if we plug in rho a equal to 0, omega a equals 0. So here's our non-dimensional boundary condition, and we see that it's the same as the first one, which is a good sign because we want 2 of our boundary conditions to collapse for a similarity solution. Finally, we turn to our second boundary condition where we plug in z equal to 0, t all values of t, and when we do that, eta equals 0. Plugging in rho a naught into our value for rho a, we get rho a naught over rho is our value for omega. So omega a at 0 is rho a 0 over rho. And we're just going to simplify this slightly and call it omega a naught. It's just a constant, right? So at this point, we've non-dimensionalized our equation, we've non-dimensionalized our boundary conditions, and because 2 of our boundary conditions have collapsed, we've shown that a similarity solution is possible. So in the next video, we will solve this equation. Thanks for listening. See you soon.